Hi everyone. I've got a little bit of a different kind of thing today to show off on the channel, but I have been working on a new Redstone design and it came together last night. And this is still a very preliminary version, but I figured I'd show it off just to show that it can be done. So what you're looking at is a rail-based 4-bit CLA adder. What that means is that this is essentially a device capable of doing addition in Minecraft, and it does that using CLA, or carry look-ahead logic. I have not seen a CLA rail-based design before, and that's not to say that this is anything to write home about. Compared to the Dust Designs and ICA and CCA editors, this is incredibly slow and very inefficient, but the fact that it can be done is part of the fun, and really I wanted to build this just to see if it could be done. So here it is. I'll show you it working first, and then we can go over what actually is going on here. So just as a test edition to show that the carry logic works just fine, we've got 3 plus 5 entered here. I'll show you how this all works in a little bit. But if we go ahead and start it up and we run over to the output, you'll see that we do get our 8. So 3 plus 5 in fact equals 8. So the timings are all adjusted so that this specific version of it works just fine. So if we talk briefly about the segments that we've got right here, this whole general area right here is the first half adder. So there's your XOR gate and there's your AND gate. And then this is where all the magic happens. This is where all of the CLA logic actually occurs. So what I have here is basically a stack up of multiple AND gates. Because of the way that the CLA logic works when you actually do the logic expansion for each one of the combinational steps. This is basically the platter where all of these signals are sent to where they need to be. And because I need to do multiple AND gates for the different signals, you can see that I duplicate the signals multiple times. For example, we've got P1 through P3 here for the very first bit, or excuse me, for the very last bit, that fourth bit, because it's going to require all of those things. But you can see as we go down the line, we're going to duplicate those signals multiple times. So if you look at the XOR gate here, obviously you get your propagate signal out. So this is 0 through 3. The other one is down here just because it has a little bit of a different architecture that's needed. But if we just look at P0, for example, you can see that it goes all the way just to the place where it needs P0. And then, for example, P1, you'll see an observer right here, as well as an observer right here. An observer right here to give both of the lines that need the P1 signal the proper signal. So this sort of top bit is just a little bit of busing. You can see that the generate signals come up from the bottom as well. And the reason why the generate signals are down here is because it also is needed for the final step in the OR gate at the bottom here. So what you see is the distribution of the propagate and generate signals up to the top so that the AND gates can be properly triggered. And then after that gate delay, which is sort of represented right here, then you get these AND gates propagating onto an OR gate in the bottom, and that OR gate is then what's fed to the final XOR module to actually compute these sum bits. Note that this is 4-bit, so we do have a potential place for a carry in here, as well as a carry out. That's really just strictly the way that this works because we've got C1 through C4 here, and we would have to have C0 coming on this side. Note that there's also a place for C0 in the carry look-ahead logic, as there's supposed to be. I just currently don't have anything attached to it, but it should function just as well. Obviously, you're going to get into a little bit of a snafu with timing delays between this and there, but ideally what you would have is you would have the signal up here that would make its way down to this location and be just as fine. But one of the interesting things to note about this design is that it is 4 wide. So all of the observer logic that I like to build is 1 wide tileable. And obviously when you look at the business that goes up on here with signal routing as well as down here, you're not going to have an identical design over each of the tiles. But importantly, what that means is that they can all be used together. So even though I've got sort of this varying build, I don't know what to call it, strategy of actually routing these signals, it still means that they're all tileable and all working together. Obviously, the weirdest part here, when you're doing a 1 wide tileable design, is that the carries that you generate at the output of the CLA logic are bit shifted by 1. So right, this is our essentially our 0 slice right here. But what we're getting out of that is the carry for the first bit. So this is C1 generated from P0 and G0, and likewise all the way down the line. So that's why we need to have this little shifter here that basically just moves it over by 1. Now note that this is not explicitly tileable because you need the multiple blocks to do it in, but I was able to fit pretty much all of the logic that needed to be fit into this 4 wide slice here. So I find that quite impressive, and I think that it's really cool that this is able to be done. So that's just sort of the 1,000-foot view of what this machine does. I just wanted to quickly show off that this is a thing that can be done. At some point, I may consider trying to compact this, trying to make it a little bit faster. Obviously, you can see these big banks of observers, and there's only a certain amount that can actually be fixed here because of the inherent gate delay in this AND gate design. But I think there are definitely things that could be fixed. So, but yeah, that's what I've got for here. So thanks for watching, and let me know what you think in the comments if you have any ideas for how this might be improved. Thanks so much.